Welcome everyone to the February 17th OMR Architecture Meeting. Today we have one topic, and it's a compiler topic. So Kevin Dean will be talking about a compiler memory leak that he and his team have discovered and would like some deeper insights on. So I'll turn it over to Kevin to take us through it.
Great. Yeah, thanks, Dale. Let me, if you don't mind, I'll share my screen here for some slides. Can everyone see the slides okay?
Yep.
All right, cool. All right. So the context here, as Daryl said, is we encountered a memory leak while working on a project that is beginning to consume the OMR code for the first time. So the project that we have is a we call it a kind of a generic non-Java front end. It's actually built on kind of an earlier version of some of the same code that OMR originally came from. So what we've been doing is progressively replacing older compiler backend components that we originally had in our project with OMR code, and of course with our kind of project-specific extensions where we need them. So in the process of doing that, recently we began consuming the memory related files. So this includes TR memory, but also kind of all of the other memory management related files from the env directory. So we're using region for the first time in various components throughout our code. For the sake of what we're talking about here today, that includes the NodePool, to some extent the compilation and the CFG. Those will be the kind of the relevant ones. All right, so let's show you what we encountered. So we recently changed over from an older version of the NodePool, more or less as it once existed in the OMR project itself, and it still existed for up till recently in our code base, and began using the NodePool that is found in OMR. Now, the original NodePool that we were switching away from was using a CS2 data structure, the table of, that was backed by a TR allocator. We still see some of these floating around in some places, but for the most part, they're kind of on their way out, I think, if they were deprecated. That is now been replaced in the new NodePool with a TR region. So when the NodePool is used to allocate nodes, what we had been using previously was this TR allocator by way of the CS2 table of. So that's all coming from a region now. We'll come back to case 2. We have it kind of as sort of a supplemental case if folks are interested. But we'll start kind of on case 1 and come back to it. But the story is similar, in which we replaced some older allocators in the CFG with the region. What we encountered was that after starting our regular regression tests, so this is after replacing the NodePool, after starting regular regression tests, within a few hours we were encountering out of memory related crashes. So we started investigating this and ran our some small kind of unit tests under Valgrind. And so what we have here is a stack trace from Valgrind that is kind of representative of a bunch of similar stack traces that we were seeing related to the NodePool. So what we're looking at is first beneath this there would be some front end kind of ILGen code that results in the creation of a node. In the process of creating that node, the NodePool is asked to allocate. This region is a member of that NodePool, which we'll look at in a little more detail shortly. So that region then is asked to allocate segments that then kind of follows down the chain of the segment provider. So we have the system segment provider that then asks the raw allocator to allocate, and finally what we end up with is a malloc. So what this Valgrind result is indicating, of course, is that we have uh, memory that's being allocated under the auspices of this particular region, that's resulting that's being mallocked at the end of the day. Um, and then there is no corresponding free. That memory is getting lost. So then the question was, why is that happening? So we took a look at that. Okay, so the node pool exists, and this is as the code exists in OMR. So the node pool is being allocated and stored as a pointer in the compilation. So we have an instance of the compilation that's created, and eventually, it will go out of scope and have its destructor called. But the node pool instance is a pointer to node pool inside of that compilation. So we can see down at the bottom here a snippet of showing how the node pool is allocated within the compilation. We have this compilation nodes member of the compilation class that allocates a new node pool. I didn't show the node pool constructor here, but the gist of it is that so the node pool has this region member called the node region, and you'll notice it's not a reference, right? So this node region is created in the constructor of the node pool using the heap memory region as the prototype to it, so as the parameter to the region's constructor, but it's not itself a reference to any other region. So this is its own region. All right, so then when the node pool is allocating nodes, they're coming from they're using this region member to allocate them, like we saw in that the stack trace from Valgrind. So useful maybe as kind of a refresher of what the region destructor does. So when the region has allocated segments, it's keeping a list of these segments that it owns, so to speak. And when the region is destroyed, it will release each of these segments in turn. So it'll walk through its list of segments and ask its segment provider to release them. In this case, what that means is the system segment provider is going to call the deallocate function from the raw allocator, and that's basically a wrapper around free. So those mallocs that we saw in the Valgrind stack trace, when a region goes out of scope, normally what should happen is those have a corresponding free called from that gets called eventually from this destructor call from the region. So in this case, that wasn't happening. So I've already begun to indicate why that was not happening, but just to sort of explain that in more detail. So what happens is that the node pool again, a pointer member of that class. So because that's the case, when the compilation goes out of scope and has its destructor called, this here is what the compilation destructor looks like, right? It's just a sort of a default constructor, destructor rather. And what that means, right, is that this compilation destructor will, by its default behavior, call the destructors of any of its non-pointer members of the compilation class, but it's not going to do that for pointer members. So as a result, the compilation destructor doesn't call the node pool's destructor, right? What happens then, of course, is that the node pool, having not had its destructor called, doesn't call the destructor of its node region. So that region member of the node pool never has a destructor called. So the memory that was allocated using that region never gets cleaned up, which leads to our memory leak. Okay, so I'm going to pause here. I do have, so we can talk more about the CFG case, which is quite similar actually in terms of what it looks like. But I want to sort of stop at that point and let people kind of jump in with questions or other kinds of discussion related to this, right? So the yeah.
Looks like you just skip one slide.
Oh, I missed one. Sorry. Yeah, you're right. Okay, thank you. So before I do that, before I stop, let me finish my story. As James pointed out, I skipped right through this slide. So the question that this kind of raises, right, is do we want this the solution that we came up with? So the solution is as kind of implied by what I talked about before, to be a task that a front end that's consuming OMR should implement. And if not, how do we want to document that or that kind of thing? So what we did to clean this up, right, is that the destructor for the NodePool needs to be called inside of the compilation destructor. So if we do that explicitly because it's a pointer member, that will then trigger the destruction of the NodePool's region. So we don't have to actually do anything to the node with the NodePool's destructor. We don't have to write any explicit destructor for the NodePool. Its default compilation compiler provided destructor will do what we need it to do, which is to call the destructor of that node region. And then as we saw, right, when that node region's destructor is called, it will free up the memory that it had allocated. And that clears up the memory leak. So this sort of provides the solution to, at least as far as our front end's use of the code is concerned, to the leak that's coming from the NodePool's region. To the question that is sort of at the top of the slide, should the solution be a task of the front end? The corresponding sort of question is that, right, if that's the case, and it may be, one thing to note is that there may be other class members that have similar sort of situations. So I mentioned that we have a second case involving the CFG that looks pretty similar to this one, kind of the same thing. There may be others, but these are the ones that we've encountered so far. And in each case, so here, that we're showing this code at the OMR level, OMR compilation. But of course, this isn't what exists currently in the OMR code. So this would either have to be implemented at the OMR level, or in each case, right, a project extension would have to take care of performing these destructor calls, or whatever other similar solution someone might want to come up with. Okay, so with that, I will get back to what I had erroneously said before, which is that I will stop there and see if there's any questions or thoughts that people have.
Hi, this is Erwin.
Hey.
So the way this whole memory infrastructure was designed, I think, was very much I think with how Java was doing things.
Yeah.
And so the idea there was that you would have, these little compilations of the different methods you're trying to compile dynamically. And so the way it worked was that you didn't need to worry about destructing the node pool. If Java never used it, but let's just say we did. Because the system segment provider would go out of scope at the end of what was known as like a compilation unit. And then for our next compilation, another system segment provider would be instantiated. And so because of that, when the system segment provider went out of scope, it would free all the segments and you wouldn't have a memory leak. And I mean, that still happens in OMR too. If you look at the destructor of the system segment provider, I mean, it doesn't do anything explicitly, but it has an underscore sets, or sorry, underscore segments member, which is an STD set. And so when the system segment provider goes out of scope, it would destroy that. Now, that's just the way it was designed based on how Java was doing things. And that, I think, was the assumption of how all this worked. Now, the question you're asking essentially, which is, should that be how OMR does it for generic languages, is something that I think has never been that's something that should be considered.
Sure.
Like, you know, should a consuming project be responsible for, you know, arranging their compilations such that, you know, the system segment provider goes out of scope, or as Devin was saying offline was, you know, should it be expected or reasonable to assume that you can have one system segment provider and you have multiple compilations based on that? So, but I just the reason for the way things are is because of that mindset of system segment provider would be there'd be one system segment provider per compilation unit.
Okay. Yeah. Yeah. Which makes sense, and certainly in that context for sure.
If we wanted to be able to rely on the system segment provider to clean it up as it does in OpenJ9, we would have to modify the destructor to actually free those segments. But I guess it's up to whether whether we want to do that or whether we want to you know, go around calling destructors or
Right.
that sort of thing. I guess my intuition is that for things that are about as long lived as the compilation, it's going to be a lot less error prone to just free all the segments at the end than to make sure, oh, did we call this one? Did we call that one? Oh, we forgot this one. And then, you know, this will happen again.
Yeah. Yeah. That makes sense. And so in that context, we have the system segment provider. Basically, the expectation is then that the system segment provider is doing it lasts for one compilation and then is replaced with another one, so that it's the memory is getting freed in between each compilation that way. Is that right?
Yeah, so that's what we do in J9,
Okay.
and that's the reason why we haven't encountered this leak, as far as I can tell.
Right. Sure. Yeah. Okay, that makes sense.
So I think if it seems if that doesn't seem like too restrictive a rule, I feel like that might be the most robust way to make sure that all the memory is cleaned up at the end of a compilation.
Yeah, I think we had a discussion at some point, perhaps as part of our earlier discussions almost a couple of years ago now on refactoring some of the memory allocator infrastructure in the compiler, where we really wanted to favor more that approach where, you know, we wouldn't be reliant on destructors being running. We would really just sweep the memory away when we were done with it. So I think that was the model that we had decided we wanted to go to. So I agree with what Devin's saying here, with that being the preferred approach and solution in this case. Now, having said that, though, if that is what we want to do, I think that we need some big fat documentation somewhere that really describes, you know, this is how it should be if you're implementing something that's consuming the compiler technology, and you know, this is how your memory segment should behave per compilation. Now, if we had if you redesigned it so that you would have one segment per compilation, would that solve your other problem with the CFG?
Or segment provider, do you mean?
Yes.
Right. Yeah. Yeah. So if we have one segment provider per compilation, you know, interestingly, I think I had toyed around with that, but I didn't know at the time that was, you know, how things were handled in J9. And so I didn't toy around with it enough probably to come up with a good answer. I would like to toy around with it some more now, knowing that. But if we're able to replace the system segment provider between each compilation, I mean, that should solve that problem if the yeah, because it's got the set of segments, which would obviously, if that's going out of scope and getting destroyed, that should clean up all of that memory.
Right. I'll just want to repeat that if you had been doing one system segment provider per compilation,
Yeah.
and that at the end of the compilation, the system segment provider went out of scope. At the moment, the OMR system segment provider would not actually release the.
Okay, that's why.
Like
Okay.
you still would have seen a memory leak.
Yeah.
So it's just deciding which way to fix that memory leak, and if we think that we
I
should
see.
put that logic in, because when that's happening in J9, it's because we have a J9 specific system segment provider that we use instead that does
Okay.
do that.
Okay. Yeah,
Um,
that makes more sense.
and it would be, I guess, a few lines of code to make the OMR one also do that. But
Mhm.
you would not have stumbled upon that solution
Right.
by in
Right.
a way like serendipitously.
Right. Yeah. Okay. Yeah, that makes more sense because I was thinking to myself, I swear that I had tried like making sure I got rid of the system segment provider each time between the compilations because of course that's at the bottom of kind of that memory stack or almost all the way at the bottom. Um, but yeah, that makes more sense. If there's something specific going on in J9 to have that happen, then that's why I wouldn't have seen that as a solution right away.
So that is actually what JIT Builder is doing. It's also it's allocating a new system segment provider when a method builder gets created, and then when that method builder's memory is destructed, then the system segment provider is also destructed and deleted.
Mm-hmm.
But I guess we're still like JIT Builder still susceptible to this issue, is what I'm grokking from what Devin just said.
I thought that so the segment is a STD set. When the STD set is destructed, what does it do? Doesn't it go and free all of its elements?
So it'll destroy the set, but it won't. I don't think it'll actually free the backing memory of the segments, right? There's explicit code that we have in.
Well, yeah, but that's because
Depends what's in the set.
in
right?
in J9 it does things using it doesn't use. I mean, I think J9 does things considerably differently. When it allocates, it uses the segments in a way of keeping track of segments or something, but
Yeah.
that's
So
not.
the segment set here contains memory segment. And so TR memory segment is defined in OMR, and its destructor is empty. And it just has a raw pointer to the memory, so there's no smart pointer in behind that that's actually doing something in the destructor.
Yeah, so the documentation of STD set says that the destructors of elements are called and the used storage is deallocated.
Yeah. But this is akin to a set of pointers, right?
Okay,
Right.
that was going to be my question. Yeah.
Like if you had a set of pointers, you allocate a piece of memory, you have a pointer, you put it in the set. Destroying the set doesn't deallocate the memory that it was pointing to.
But it's not a set of pointers. It's a set of
No, it's a set of memory segment, and if you
which is a
look
pointer.
at compiler/env/memory segment.hpp, it just has a raw pointer to it and an empty destructor.
Mm.
Yeah.
Right.
But anyway, what we have in J9 is a loop that's, like maybe a few lines long. It's really not a lot of code to free these things.
Yep, that makes sense. So I think probably the question for consuming projects is more if that's the preferred way of doing it, which makes plenty of sense, probably to have some kind of documentation at the OMR level, as Daryl was maybe suggesting.
Yeah, and for it to be implemented at the OMR level, because I do think it sounds like JIT Builder is susceptible to this problem at the moment.
Okay. Yeah.
So couldn't the actual freeing of the memory be addressed by just updating the destructor of memory segment to deallocate?
I'm not sure where else that gets called. Well, like for example here, when we're inserting into the segment set, we construct a TR memory segment and we pass that into insert, which I presume copies it, and then we'll destroy the temporary, and that would probably.
Right. So we're copying. Okay, so you're right. So then system segment, or the system segment provider, is probably the right place to manage, like the destructor of system segment provider is probably a better place to manage that.
Yeah, I think so, and it makes it clear when it happens too. As opposed to, oh well, this is a consequence of, there's this and that and that and that and that, and then if you think about it, then you can figure out when it happens.
You mean like C++ code? Oh, sorry.
Yeah.
I'm sorry, was someone going to say something?
No, I was just going to say if that's the resolution here, I guess we should find the code that's in the corresponding J9 segment provider and lift that into OMR.
I don't think you can just lift that code because it's quite different in J9. But it's gonna have to be like OMR is gonna have to have its own version of it, but it's still, I think, what Devin said, like maybe 3 or 4 lines. Because in J9 the art, like the way these things are composed is different than OMR. That's one of the reasons we had that proposed memory changes, is to keep things consistent.
Right.
Yeah, and the destructor, it's just looping at least the version of the code I'm looking at, which could be older, but I don't think this changes very often. It's just a loop over the system segments and calling a release from the system segment allocator. So you're right, it's not quite the same, but it'll be pretty close.
Okay, so Kevin, how do you want to proceed here? Do you want to take a stab at making the changes, or do you want someone that's a bit more familiar with the code to do that? If it's just a matter of adapting what's there, maybe that's something you could take on. But if not, we know. Okay.
Yeah, I think that would be fine. If I have any trouble figuring out adapting it, then I'll certainly reach out to somebody, one of you guys. But I'd be happy to sort of take that on as a something I can contribute here, and then we can test it out at our level and confirm that we're seeing the solution we expect. And yeah.
Okay, great. That sounds good. All right. So, I mean, while you have this distinguished panel of experts here, do you have any other questions on allocation or things like that?
Yeah, I don't know if James, did you want to bring up what you had mentioned about the cursor?
Yeah, sure. We kind of completed the discussion for the case one. Now, yeah, we can talk another case. It's at the beginning we have a similar solution for this one. But yeah.
Let me I can share this screen properly. Sorry. Okay.
So yeah, thank you. So let me try introduce something we find for the case two study. It's again somewhat similar memory leaks, definitely lost from the background. This case is happened when we call the it's actually invoked by the compile method and calling to perform the optimization. And we from the stack trees we see it's go back to cursor, then finally some to the raw allocator again the malloc, and we find out that the memory is totally lost, never get freed. Next slide, please.
Sure. So one thing I'll point out here, James, just to not make you have to repeat too much for this part is like this story here basically is similar, right? About the road here leads back to a region in the CFG, basically is the
Right.
is the memory leak story here, which in the end kind of looks the same as the NodePool situation, right? So there's a region in the CFG that's being used to allocate. In this case, what we find is, so we have this type deft vector of subgraph node pointers that's backed by what turns out in the end to be this structure region from the CFG. And for the same reason as the NodePool causes a leak, right? This will end up having a leak because the CFG is stored as a pointer inside of the resolved method symbol, which is stored as a pointer inside of the compilation again. One thing that James discovered, though, was, and I think had a question about, was related to not just that memory leak per se, but also to the use of the cursor more generally, I think. Is that true, James?
Right. Yeah.
I
And
can skip ahead too. So yeah, just to sort of this this part of the story is kind of the same as what we saw before with the NodePool, right? So in the end, these destructor calls could be done as we've talked about. We can probably handle this with the system segment provider changes that we discussed. But there's also the James had worked on a sort of another workaround, and I think had a question about some of the way that the cursor is doing a copy. So James, I'll give it back to you there.
oh yeah, thank you. Yeah, what we concern is about it says the cursor is actually provide a immutable view of the underlying elements, and to achieve that, it's the cursor itself is actually must copy the elements from the subnode list listed before, and it is of course a adding a non-trivial cost for this one. So I'm thinking, is that possible? We want to check the value of the underlying elements, and to avoid accidental modification of all any elements of that subnode list, we create the cursor. However, what if we can directly access those elements inside the subnode list, and if we are sure we don't modify them, then functionally looks like to me the same thing. And so I made one experimental test, and elements and check the results. Then the memory leaks is gone, and probably we can save some additional the cost of the copy. And but the thing is, this is experimental test. I didn't really ensure I'm using any const accessor to ensure the elements is non-modified or whatever. And the other thing is we have to, if we are using this approach, we may have to replace the cursor or get rid of cursor. It's not just in one place, in multiple places. Like in structure, we have a method initial structure, and there's a method, I think it's a reset structure, something like that. We can again to replace the cursor and a few other places possibly to use this approach. So we show this alternative solution here just for further discussion, especially in front of experts to guide us. Is that reasonable or something worth of thinking? So yeah, that's basically what we did, using the directly accessor to access element of the region structure, but not using the cursor to make a copy, then check the underlying elements. That's an alternative solution.
Okay, so I guess there are kind of two things here, right? So one is that I think this is kind of, but kind of not covered by what we talked about in the other case with the NodePool.
Mm-hmm.
In that that'll prevent these things from outliving the compilation, but if we don't want them to, it's possible that they're living a lot longer than they need to within the compilation, and that could be, adding up to, a lot more memory usage than needed, depending. And then so there's avoiding extra copies, which I guess are also allocating into that same region, is it?
I think so, yeah.
Yeah. And then there's also maybe we want to just get rid of some of these things. I've been trying to look at memory usage during a compilation, and part of the thing is that tons of the regions that we're creating and some of the methods I'm looking at are well, I think that they're related. They're probably this region. I don't know for certain, but basically they're getting created during inlining, and more specifically during ILGen during inlining. And now I don't know how much actual memory we have total in those ones yet. But if it's a significant amount, then that's a separate thing where I don't think any of these are needed afterward. Like say once you inline some other body into wherever it's going, well, it doesn't need its own CFG in its own structure region anymore. We're not going to go look at those things. I don't think. So there's that. And then what I'll say about avoiding copies with this iterator is that I think it's fine to have such an iterator, but that I would be pretty wary of getting rid of the one that makes a copy and blanket replacing it. Because it does make a copy, it may not be obvious where we're relying on that defensive copy and where we're not.
Yeah, that makes sense.
Yeah.
Good. So, James, did you have anything else about that one? That you
Yes,
wanted to...
that's fine for me because yeah, because I have only limited understanding of the code base and only read the code. We get in touch quite a few files, but not much, right? We don't have a high level view of the OMR code till the moment. It's just case by case. We encounter something, we take a look. Yeah, that's it.
Okay, so these two are were the most significant memory leaks you found?
Yeah. In fact, once we had cleaned up these two, so this in the second case, right? It was there were a variety of leaks that were all kind of related, coming from this region. So the cursor example was one of them, but then there were kind of others that were where this region was being used for other allocations. But once that's cleaned up, then it takes care of all of those leaks. So between this and the NodePool, those were the sources of all of the memory leaks that we were seeing. So
yeah. This one is like inside the perform optimization. It's a recursive call, and another case is somewhat similar. Again a recursive call when we initialize or reset it. So we are creating huge amount of memories leaks. Once we use the solution, or yeah, so then we don't see the memory leaks.
yeah, okay. So I think we have I mean, it sounds like there's a useful way forward to try adapting this the J9 system
Right.
segment providers cleanup to the OMR system segment provider, so that we can give that a shot and see if that takes care of the issue. And probably we'll have to do some adapting on our end also to make sure that the system segment provider is created once and going out of scope for each compilation. But yeah, I think that makes sense.
Yeah, thank you.
Okay. Any other comments for Kevin or James on this topic? Okay. All right. So this was the only topic this week. So thank you everyone for your participation, and good to see that we had I think a successful resolution of this problem. So thank you. And we'll convene again in 2 weeks.
Thanks very much,
everyone.
everybody.
Bye.
Thank you, everyone. Bye.
All right.